The universe is not a random accident of drifting rocks and blind collisions. It moves with structure, rhythm, and intent, like a vast symphony written into the fabric of space itself. But on March 5, 2026, at exactly 6:22 UTC, that symphony is expected to strike a note so precise, so unsettling, that it may force humanity to confront a failure in the planetary protection rules we have trusted for decades. An interstellar object known as 3I Atlas, a 33 billion ton mass of frozen complexity, is now racing through our solar system on a trajectory that cannot be explained by chance. This object is not drifting, it is not wandering. According to telemetry and orbital modeling, it is aiming. Not at Mars, with its dead surface and thin air, not at Venus, with its crushing heat and corrosive clouds. Instead, the calculations point toward Ganymede, a moon uniquely optimized for life. Ganymede is the only moon in the solar system with its own magnetic field, and one of the very few bodies beyond Earth known to possess a detectable oxygen atmosphere. The odds of an interstellar object naturally selecting this destination are astronomically small. What we are seeing is not coincidence, it is intent written in mathematics. In celestial mechanics, the Hill radius defines the region where a planet's gravity dominates over the Sun's influence. For Jupiter, that boundary stretches roughly 53 million kilometers into space. On November 23, 2025, analysts calculated that 3I Atlas would cross this exact boundary on March 16, 2026. When simulations were refined, the final approach aligned with Jupiter's Hill radius to within just 57 kilometers. Out of tens of millions of kilometers, the margin of error was less than the width of a city. In probability terms, that level of accuracy is nearly impossible without active guidance. This is where the implications become impossible to ignore. If we apply advanced models of civilizational capability, this kind of navigation suggests something far beyond natural motion. It implies deliberate course correction across interstellar distances, the ability to guide a massive object through the gravitational currents of space with surgical precision. This is not the behavior of a comet. It is the behavior of a craft. The destination matters. Ganymede should be geologically dead. A moon of its size should have cooled and solidified billions of years ago. Instead, it remains internally active, with a molten metallic core generating a magnetic field strong enough to carve out a protective bubble within Jupiter's lethal radiation belts. This magnetic shield produces auroras, shimmering bands of light around the moon's poles, confirming an internal dynamo still at work. That same shield makes Ganymede one of the safest environments in the outer solar system for complex chemistry to persist. Even more unusual is its atmosphere. Ganymede contains molecular oxygen and ozone, gases that should not survive for long without constant replenishment. The standard explanation is radiolysis, radiation breaking apart surface ice, but oxygen is highly reactive. It should disappear unless something keeps producing it. On Earth, free oxygen exists because life continuously replaces it. When oxygen persists, biology must at least be considered. Now connect that environment to what 3I Atlas is carrying. Spectroscopic analysis reveals methane levels far beyond those seen in ordinary comets, alongside carbonyl sulfide, a compound closely linked to biological processes. Most striking is the enrichment of carbon, 1,3 isotopes, a known signature of biological carbon processing. These are not random chemicals frozen in ice. They resemble a curated inventory. All evidence points toward a single conclusion. 3I Atlas is not just passing through. It is approaching the one world in the Jovian system capable of sheltering life delivering chemistry shaped somewhere far beyond our Sunday, and as it closes in on Jupiter's gravitational boundary, the music of the spheres is no longer background noise. It is the sound of arrival. That arrival forces us to confront a question NASA has so far avoided addressing directly: why Ganymede and why now? To understand the tension surrounding this trajectory, we have to look beyond orbital math and into the rules that govern life, energy, and disorder in the universe. At the heart of the concern lies the second law of thermodynamics, the principle that all closed systems drift toward equilibrium unless something actively intervenes. Dead worlds stabilize, living worlds do not. When scientists examine atmospheres across the solar system, they expect chemical balance. Reactive gases should neutralize each other over time, leaving behind a quiet, inert mixture. Yet Ganymede refuses to fit that model. Data from earlier missions revealed persistent molecular oxygen and ozone lingering above its icy surface. Oxygen should not survive long in contact with ice, rock, and trace carbon compounds. It should disappear unless something keeps producing it. Radiation alone struggles to explain the measured concentrations. The numbers simply do not close. This is where the silence becomes meaningful. If Ganymede's oxygen exceeds what radiation can reasonably generate, then an alternative explanation must be considered. On Earth, oxygen-rich environments exist only because life constantly replenishes them. Biology pushes systems away from equilibrium, it fights entropy, and now, an interstellar object carrying biologically suggestive chemistry is lining up with the only moon in the Jovian system that already shows signs of chemical imbalance. The chemical inventory of 3I Atlas deepens the mystery. Observations reveal hydrogen cyanide production at levels several times higher than those seen in typical comets. In prebiotic chemistry, hydrogen cyanide is not a side note. It is foundational. It participates in reactions that build amino acids, nucleic acids, and the molecular scaffolding of life. Add to this the elevated methane levels and the presence of carbonyl sulfide, a molecule closely associated with sulfur-based metabolic pathways on Earth, and the pattern becomes difficult to dismiss. These are not the random outputs of frozen debris. Together they form a toolkit, a prebiotic package capable of jump-starting chemistry under the right conditions. And Ganymede offers exactly those conditions: liquid water beneath its ice, protection from radiation, internal heat, and a magnetic shield that preserves fragile molecules long enough for reactions to occur. This raises the possibility that 3I Atlas is not merely carrying chemistry by accident. It may be transporting it by design. Interstellar panspermia, long debated as a fringe hypothesis, begins to look less speculative when the delivery vehicle demonstrates intentional navigation and chemical selectivity. If life can spread between stars, it would not do so randomly. It would target environments where success is most likely. Ganymede is strategically perfect. Its surface gravity is low, making it easier for material to settle rather than burn away. Its subsurface ocean is vast, potentially holding more water than all of Earth's oceans combined. Its icy crust is dynamic, fractured, and capable of cycling surface material downward over time. Anything deposited on the surface does not stay there forever. It moves. This is why planetary protection protocols exist. Any spacecraft sent to worlds like Ganymede must be sterilized to extreme standards to avoid contamination. Yet 3I Atlas is not subject to those rules. It is venting material freely into the Jovian system. If fragments separate as it passes through Jupiter's gravitational domain, they would not need engines to reach Ganymede. Gravity alone could do the work. NASA's reluctance to redirect existing spacecraft for closer observation begins to make sense in this context. Confirming biological delivery would trigger legal, ethical, and scientific consequences beyond any mission's original scope. It would mean acknowledging that humanity is not controlling the biological timeline of its own solar system. As the approach window tightens, the question is no longer whether something unusual is happening. The question is whether we are witnessing the first documented case of life-bearing material being intentionally delivered across interstellar space. And if that is true, then Ganymede is not just a moon, it is a recipient. That possibility forces the discussion into uncomfortable territory because once delivery is plausible, intention can no longer be ignored. If fragments from 3I Atlas enter Ganymede's orbital space, their journey does not end in the vacuum above the surface. Ganymede's exosphere is thin, but it is not irrelevant. Molecules that arrive there do not remain suspended forever. Over time, they settle, freeze, and migrate downward. This is basic atmospheric physics. Gravity may be weak, but it is relentless. Beneath the ice, the real story begins. Ganymede's subsurface ocean is buried under nearly 100 miles of crust, yet it is not sealed off. The moon's surface is geologically active by icy standards. Cracks, ridges, and zones of resurfacing suggest constant slow recycling. In cryovolcanic systems, surface material is pulled downward over long timescales, mixed with liquid water, and redistributed. This means any complex chemistry delivered to the surface does not stay sterile. It is eventually introduced into a warm, pressurized, liquid environment. That is why the timing matters. The passage of 3I Atlas through Jupiter's gravitational domain is not a casual flyby. The precision of its trajectory suggests careful planning. A 5-7 kilometer margin, after traveling trillions of miles, is not noise. It is targeting. If fragments are released at the correct velocity, they do not need propulsion. Jupiter's gravity becomes the delivery system, slowing them just enough to remain bound while guiding them toward Ganymede's path. This is where orbital mechanics intersects with biology. The slow rain of material onto an icy surface may sound harmless, but chemistry does not require force. It requires time, contact, and stability. Ganymede offers all three. If hydrogen cyanide, methane, and sulfur-bearing compounds reach the ice, they can survive long enough to be carried into deeper layers. Once in contact with liquid water, reactions accelerate. Complexity increases. Entropy reverses direction locally, exactly as life demands. The carbon isotope evidence strengthens this concern. An enrichment of carbon, 1,3 relative to carbon, 1,2 is not random. On Earth, biological systems preferentially consume lighter carbon, leaving heavier isotopes behind. When that pattern appears in extraterrestrial material, it suggests prior biological processing. These molecules are not raw ingredients. They may be leftovers. Metabolic remnants preserved in ice for eons, now reintroduced into a new environment. This reframes the role of 3I Atlas entirely. It is no longer just a carrier of potential. It may be transporting biological history, not organisms in the familiar sense, but molecular fingerprints shaped by life elsewhere. If those fingerprints mix with Ganymede's ocean, the result would not be contamination in the traditional sense. It would be transplantation. That is why the silence feels deliberate. Observing this process too closely could force acknowledgement that the outcome is irreversible. Once chemistry enters the ocean, there is no undoing it, no quarantine, no sterilization protocol. The experiment runs to completion, whether we approve or not. The implications extend far beyond one moon. If life can be seeded intentionally across star systems, then biology is not rare. It is managed, distributed, cultivated. Ganymede may not be special because it is close. It may be special because it is ready. As the intercept window approaches, the language of discovery begins to fail. This is not exploration. It is observation of a process already underway. Humanity is not the actor here. We are the witnesses, trying to interpret evidence while the event unfolds on its own schedule. The deeper truth is this. Once delivery begins, the question of whether Ganymede hosts life becomes meaningless. The only remaining question is when that life begins to change the moon in measurable ways. And by then, the cause will already be gone, moving on to its next destination. By the time that realization settles in, the event has already moved beyond speculation and into the territory of planetary protection law. At the core of that framework are the guidelines established by Committee on Space Research, which define how humanity must behave around worlds that could host life. Moons like Ganymede fall into the highest risk category, not because we have confirmed life there, but because the environment makes life plausible. Any spacecraft sent to such worlds must be sterilized to an extreme standard, reducing the chance of carrying even a single Earth microbe to near zero. These rules exist for one reason. Once contamination occurs, it cannot be reversed. And yet, none of those safeguards apply to 3I Atlas. It is not a probe launched from Earth. It did not pass through clean rooms or sterilization chambers. It is a 33 billion ton interstellar object venting complex chemistry directly into the Jovian system. If fragments separate during its passage, they are not violating policy, they are bypassing it entirely. This is what makes the situation unprecedented. The rules were written for human technology, not for non-human delivery systems. This context casts a new light on the decision by NASA to avoid close-range observation. Officially, the explanation centers on mission priorities and fuel limitations. Unofficially, the risk is obvious. Direct evidence of fragment release or engineered deceleration would force a classification shift. It would mean acknowledging a non-natural actor altering a potentially habitable environment. That acknowledgement would trigger international protocols that no space agency is prepared to manage in real time. The irony is that the observational capability already exists. The Juno spacecraft, currently operating within Jupiter's system, has the instruments needed to detect changes in particle flow, unusual emissions, or structured ejecta. Data simulations suggest it could maneuver close enough to gather meaningful evidence. The choice not to do so is not about ignorance. It is about consequence. Because once confirmation arrives, the timeline shifts. The focus is no longer on what Ganymede was, but on what it is becoming. If biologically relevant material reaches the moon's surface, it will not announce itself immediately. Life does not arrive fully formed. It emerges slowly, quietly, over thousands or millions of years. But the origin point matters. When future missions search for life, they will be unable to distinguish between indigenous biology and introduced chemistry if that introduction goes undocumented. This is where the future intersects the present. In 2031, the ESA-JUICE mission spacecraft is scheduled to enter orbit around Ganymede. Its instruments will map the surface, analyze the ice, and sample the environment with unprecedented resolution. If it detects organic compounds, isotopic anomalies, or complex chemistry, those findings will reshape our understanding of life in the solar system. But without acknowledging the events of 2026, those conclusions may rest on a false assumption. The possibility that life on Ganymede could be seeded rather than native challenges. One of the most important questions in science. Are we alone because life is rare or because it spreads? If panspermia is real, then biology is not confined to planets. It is mobile, opportunistic, capable of crossing the void when conditions allow. As 3I Atlas completes its passage through the Jovian system, its influence may already be locked in. The trajectory, the chemistry, and the timing suggest more than coincidence. They suggest selection. A world chosen not for its beauty or proximity, but for its readiness. Ganymede has the shield, the water, and the energy. It does not need much more. At this point, humanity's role is reduced to record-keeping. We can document the approach, debate the implications, and argue about intent, but the process itself is indifferent to our opinions. The delivery, if it occurs, will unfold on geological timescales far beyond human lifespans. And when future explorers finally drill through Ganymede's ice and find evidence of life stirring in its ocean, the most unsettling question will not be how it evolved. It will be why it was placed there at all. As the timeline advances toward the moment of closest approach, the discussion shifts from theory to inevitability. At exactly 6:22 UTC, on the 17th of March 2026, 3I Atlas is projected to cross the orbital region of Ganymede. This is not simply a flyby measured in astronomical terms. It is a calculated intersection inside one of the most sensitive environments in the solar system. In planetary science, proximity matters. Small changes in velocity, angle, or mass release can cascade into outcomes that persist for billions of years. The governing framework for such encounters was designed with human error in mind, not cosmic intention. Planetary protection protocols exist because we know how fragile pristine environments are. A single microbe, introduced at the wrong time, can permanently alter an ecosystem. That is why missions to ocean worlds are treated with extreme caution. But an interstellar object does not sign treaties, and it does not wait for clearance. It follows physics, and physics alone. If fragments detach from 3I Atlas during its passage, they will not need propulsion systems or guidance computers. Jupiter's gravity does the work. In orbital mechanics, this is known as a capture opportunity, a narrow window where relative velocity drops low enough for material to become bound to a moon rather than escaping back into space. Data simulations indicate that this window exists precisely during the predicted encounter. The same gravitational force that makes Jupiter a shield also makes it a funnel. Once material enters Ganymede's exosphere, the process becomes chemical rather than mechanical. Molecules like hydrogen cyanide, methane, and carbonyl sulfide do not remain suspended. They interact with radiation, with oxygen, and with the ice itself. Over time, they settle, migrate, and concentrate. In a fractured ice shell like Ganymede's, surface material is not isolated. Geological cycling slowly pulls it downward, delivering chemistry into the subsurface ocean where temperature, pressure, and energy converge. This is why the silence surrounding the event is so striking. Publicly, agencies emphasize uncertainty. Privately, the models are clear enough to raise concern. Acknowledging the risk would require acknowledging responsibility, even if no action can stop the process. It would also require reframing humanity's role in the cosmos, from explorers seeking life to witnesses watching it arrive from elsewhere. The ethical implications are profound. If life emerges on Ganymede in the future, and we know it was influenced by an external delivery, then the discovery no longer answers the question of whether life arises independently. It answers a different question: how often is it transported? That distinction matters. It reshapes how we interpret every biosignature detected beyond Earth. The presence of isotopic anomalies deepens that concern. Carbon 1,3 enrichment is not a trivial detail. In geochemistry, it acts like a fingerprint, distinguishing between processes driven by heat and pressure and those shaped by metabolism. If such signatures are later found embedded in Ganymede's ice or ocean, scientists will face an uncomfortable conclusion. The moon's biology, if it exists, may carry a record of another star system's past. This is not about fear of invasion or science fiction scenarios. It is about context. Life that spreads changes the meaning of isolation. It implies that habitable environments do not need to start from scratch. They only need to be ready. Ganymede appears ready in ways no other moon is. It has protection from radiation, abundant water, chemical gradients, and now, possibly, an external catalyst. As 3I Atlas rotates and vents its material, its influence diminishes with distance, but not with significance. The object itself will move on, continuing its journey through interstellar space. The consequences of its passage, however, remain behind. They are written into trajectories, surface chemistry, and future datasets that have yet to be collected. By the time the next generation of spacecraft arrives, the moment of delivery will be long past. Scientists will analyze what they find without having seen the act itself. And in that gap between cause and observation, certainty will be replaced by debate. The most important event may already have occurred, unnoticed except by equations and simulations. We are approaching the point where observation gives way to aftermath. The question is no longer whether something unusual is happening, but whether we are prepared to accept what it means if it is. When the encounter finally passes, what remains is not a spectacle in the sky, but a permanent alteration of context. 3I Atlas will not linger. It will exit the Jovian system the same way it entered, silently and at speed, leaving behind no engine plume, no transmission, no message that can be decoded. Yet absence does not mean insignificance. In astrophysics, the most important forces are often the ones you cannot see after the fact. Gravity reshapes orbits long after the passing body is gone. Chemistry rewrites environments long after the reaction begins. The final movement of this event is not about impact or collision, it is about inheritance. If material from 3I Atlas has entered Ganymede's environment, even in trace amounts, the moon's future has diverged from its past. From that point forward, every biological question asked of that realization, it is not just another moon, it is a crossroads. A protected ocean world with the chemistry of potential and now, possibly, the chemistry of origin from elsewhere. If life takes hold there, it will not announce itself with lights or structures. It will emerge slowly, invisibly, over time scales far longer than a human lifespan. By the time it is undeniable, the cause will be ancient history. That is the quiet gravity of this event. There is no explosion, no warning siren, no clear dividing line between before and after. There is only a subtle transition marked by numbers, spectra, and probabilities that lean too far toward intention to be ignored. The universe has played its note, and the echo is now embedded in ice and orbit.